Institute for the support and help. Today, we continue to have a very interesting program of 5 technical talks. Without further ado, let's welcome the first speaker, Jacob Andreas from MIT. Jacob.
Thanks. Let me share my screen here. All right. Is this visible?
Yes.
Okay, great. So yeah, hi everyone. Thanks, Li Hong. My name is Jacob Andreas, and I work on natural language processing at MIT. And today I'm going to be talking specifically about what we can do with language data in support of machine learning or of reinforcement learning applications. And I want to start by emphasizing that my main interest here is language. Our group is not focused on RL. I'm emphatically not a theorist, but interested in, as J.L. Austin says, doing things with words and using language data to sort of specify actions that we want real world agents to take and interact with things out in the real world. And so I want to start a little bit by talking at a high level about what the intersection of the NLP and the RL worlds looks like. And I think part of the reason there isn't so much interaction right now is that the approach to learning problems is very different. That, at a venue like this, the sort of prototypical RL problem involves a single environment equipped with a single reward function. And our goal is just to sort of hill climb in policy space until we get a good reward. Now, there has started to be interest more recently in sort of dropping an agent into an environment in which they observe some description of their goal rather than having to thrash around and figure out what they're supposed to do. And now whatever kind of training signal you get for learning this policy, it at least sort of from an NLP perspective looks like a normal learning problem insofar as there's a data set and you can start to ask interesting questions about generalization. And in particular, if these goal specifications take the form of natural language commands, then this just looks like a learning problem that we know and love in NLP, which is the problem of following instructions. And if you treat goal specifications as observations, these 2 learning problems on the bottom are just special cases of the top one. And in this sense, language can be a super useful tool for multitask RL. It gives you an expressive and flexible family of goal specifications. You can elicit these goal specifications from unskilled users without special tooling, which is a point that we'll come back to later. And you can plug them into your existing RL approaches without having to think too much about like what the language is or what it actually describes. Now, to the extent that there's something identifiable as like a standard approach to language in RL, it basically looks like this picture. That whatever linguistic annotations you have are just part of your observation space. They tell you what you need to sort of get the reward that you want. What I would like to suggest today is that this picture is at least incomplete, and to talk about a couple of other roles that language might play representationally in the broader RL landscape. And in order to do that, I want to start by actually talking about one of my favorite psychology experiments. And the setup for this experiment is as follows. We have a rectangular room with clearly distinguished long and short walls, and one of those walls is painted blue. So every corner in this room is uniquely identified by whether the long wall is on your left side or your right side, and whether by the presence or absence of this blue color. We're then going to take some sort of rewarding thing. We're going to hide it out of sight in one corner of the room. And the basic form of the experiment we're going to run here is to place an agent in the room, let them find the reward, disorient the agent, and then see if they can find it again. Now, if you do this experiment with rats, they're not very good at this task. A little less than half the time, they do the right thing. Otherwise, they go to the wrong corner or they give up. And the conjunctive aspect of this goal location is important. If the rats just have to discriminate based on position or just based on color, they do fine. Now, if you take pre-verbal human infants and you give them the same task, they're even worse. They're evenly split between the spatially equivalent corners, maybe even a little worse than chance, and again, ignoring the color of the wall. Now, unsurprisingly, if you run this experiment with sort of normal human adults, almost everybody gets it right. But if you then take these adults and you hijack their language abilities by asking them to repeat a prose passage out loud while they do this task, they start behaving like rats or pre-verbal infants. Now, this effect appears to be specific to language. If you give these people cognitively demanding tasks that don't involve language, they don't produce the same effect. So it seems that the language faculty is in some way specifically implicated in humans' abilities to form compositional representations of goals in tasks that look like this, and in particular, even for tasks that have nothing to do with language. Now, I don't want to overstate the implications of this experiment for machine learning. Obviously, current approaches to RL with a good enough function approximator do just fine at these kinds of problems without being able to speak English. But these experiments do sort of suggest that language might be useful as a representational tool in the same way that people find it useful. And again, even in those problems that, like this one we've been looking at, don't actually give you language as part of your environment observation. And so we're going to look at a couple of different views on this perspective of the problem, starting with language as a source of temporal abstractions for reinforcement learning. Now, as a running example on the next couple of slides, we're going to think about a sort of Minecraft style video game in which you have tasks like making planks that consist of steps like chopping down trees, using a workbench, and so on. Now, as we know, there are lots of reinforcement learning problems that involve high-level actions, where there exist temporally coherent sequences of actions that an agent can execute that cause a specific change in the environment or accomplish a sub-goal in a way that's useful either across multiple stages of a task or multiple tasks. Things like getting yourself to the exit of the room that you're in or grasping the object that's closest to you. In one formalization of this approach, sub-policies that implement these high-level behaviors are called options. If you have access to the right set of options, they make RL a lot easier, right? The sort of long horizon problem gets significantly contracted if we only need to take a small number of these high-level actions. But automatically discovering options is super hard, sometimes as hard as the underlying RL problem. And so there's correspondingly been a lot of work on figuring out alternative forms of supervision that we can use for inducing these kinds of hierarchical policies. The simplest thing that you can do, of course, is to manually specify subtasks and provide some kind of explicit subtask completion signal or other intrinsic reward. This makes learning easy at the cost of making sort of annotation or reward engineering really hard. Another thing that you can do is to collect examples of successful behavior provided either by an expert or by successful rollouts from the model itself, and then try to segment these things into reusable options. This problem just looks like ordinary learning in an ordinary hidden semi-Markov model, and we can sort of throw our structured prediction toolkit at it and do pretty well. So what role might language play in a process of option discovery? Well, if you think about what an instruction for one of these tasks, like get wood and then use a saw, about what that instruction does, it's basically giving you supervision for the top part of this figure. It's communicating something about the abstract structure of policies without actually specifying how this abstract structure grounds out in low-level percepts or actions. Now, this is obviously useful if you already know how to interpret these instructions. But what if you don't? Is this kind of linguistic supervision useful even to guide sort of RL from scratch? And what this looks like practically in a multitask setting is something like this. I have, say, task one. I have some high-level instruction that says first get wood and then use a saw. And initially, my learner doesn't know what either of these things mean. I have some other task that gives me high-level advice in the form of get wood and then use an axe. Again, the learner doesn't know what these things mean, but whatever this get wood thing is, it appears at the beginning of both of these sort of high-level commands, and that's an indication that the beginning of a successful trajectory for each of these tasks should look the same at this abstract level of representation. We're going to call these pieces of high-level advice policy sketches. And like we saw at the beginning of this talk, the most literal-minded thing we could imagine doing with these policy sketches is just constructing a sort of single fixed model, say a feed-forward neural net, that conditions on a representation of the sketch as well as environment features. This looks like the kind of instruction following models that we have again in the NLP literature, but taking inspiration from all the other work that's gone on in hierarchical RL, we can also imagine using these sketches to structure the parameterization of our policies themselves. And concretely, we're going to implement a hierarchical policy where there's a high-level policy that's just going to mechanically execute in sequence a low-level policy for each of these instructions, for each of these tasks. And then these low-level policies will be shared across high-level policies when the underlying instructions are the same. So this is ultimately just a structured parameter tying scheme where the structure of the parameter tying is inherited from a sort of co-occurrence in language. And I really want to stress how little information is communicated by these sketches, right? What's on screen is literally the entire file containing the extra supervision we're going to use for these crafting experiments. Many, many fewer bits than what the agent is going to get via its interaction with the environment. But even this tiny bit of extra supervision used to do this structured parameter tying makes a big difference. So we can look at this. Here's a more sort of fleshed out example from one of these crafting tasks where the agent, if it wants to get the gold brick, has to do things like getting wood and getting metal and combining them at a particular place into a bridge and then walking across the bridge and so on. We also did some experiments on learning locomotion policies. And the important takeaway here is that language helps, but specifically that using language in conjunction with an options policy, rather than just treating it as part of our environment observation, is what's really important here. And this is true whether you have these sort of discrete game style action spaces or continuous control. Now, so far we've just been looking at normal RL learning curves, right? Our agent gets to interact with the training environment as much as it wants. It's going to see these sketches in all of them, and we're just trying to make those lines go up as quickly as possible. But in keeping with the theme of sort of using language even for problems that don't explicitly involve language, we can also ask the following question. Does this kind of pre-training give us a good inventory of high-level actions that are useful for new tasks, even if we don't observe any language at all? And for context, here are the sort of final task completion rates for an unsupervised options learner and a learner with policy sketches on those crafting tasks we were looking at earlier. If we introduce a new, sort of similarly challenging task with no language at all, we can still do RL at the high level and still using these sort of low-level policy or sub-policies that we learned from language, be able to explore very efficiently in these new environments. So language plus this hierarchical RL framework lets us bootstrap policy representations that are good initializers, even for non-linguistic tasks. Now, so far we've been referring to the supervision as language. The kinds of high-level behaviors we've been talking about were in fact very simple. The annotations that specified them were basically discrete indicators. Does this generalize to what we think about when we actually talk about natural language? So here is this the data set that I want? Yeah, is an example from a data set that was recently released, or a game and a corresponding data set that was released by some folks at Facebook. It's great. It includes these sort of hierarchical instructions where you get high-level natural language annotations for sequences of subactions that are being executed by these agents as they play, right? So now there's a sort of high-level command to build cavalry that bottoms out in some low-level actions. And as a side note, it's sort of difficult to imagine how you might elicit this kind of hierarchical structure if you didn't have language as a structuring device. That in some sense, what makes this a good high-level policy is that each of these high-level actions has some sort of concise, coherent natural language description. Now, in this game, of course, we have a much richer space of natural language actions, but we can repeat that last experiment from our crafting game and ask what happens if you use a model derived from this language data as an initializer, and then do RL at the high level and at the low level. And here we have much weaker constraints, right? We're not constraining the high-level model to execute commands in lockstep, but this pre-trained high-level policy encodes a bunch of prior knowledge about what sequences of language-based commands are plausible. Note this is still a sort of, you think of it as a semi-Markov model, but now your space of options or your space of like Markov states is indexed by the set of natural language strings. Sure enough, even when the language gets much more complicated, language helps a ton. You can learn quite effectively by sort of jointly training this high-level controller policy and the model that interprets the high-level instructions. I'm going to skip this slide. Next, I want to briefly talk about one more sort of generic way of using language to guide reinforcement learning. So we looked just in the last section of this talk at ways of using it to give us kind of temporal structure in our policies. Now let's talk about using it to structure goals. And let's think back to this experiment from the beginning of the talk. The fact that only adults with unimpeded language faculties can solve this task implies that language is somehow being used to construct or help construct the goal representation. So what might that look like in a machine learning context? Well, if we're in some sort of environment where we know the dynamics and we have the ability to plan, then the main problem that a reinforcement learner has to solve is just to infer the form of the reward function. And if we're in a multitask setting, the learning problem is basically to identify some space of goal representations and parameters for interpreting those goal representations that explain the rewards that this agent is seeing on different rollouts for different tasks. And whether you're getting feedback via interaction or from a bunch of demonstrations, learning, basically reduces to inference in this kind of model. So then the question is, what does a space of goal representations look like? And nowadays, there's a lot of work on like visual goals where you just predict the sort of image that you want to see when you get to the end of the task, or sort of free-form goal embeddings. But of course, it's very easy to set this model up in such a way that goals are natural language descriptions. That while exploring, our RL agent is asking, how would I describe in language the features that are common to all of my successful trajectories? And the cool thing about setting the problem up this way is that a reward model like this is up to normalization an instruction following model. It picks up a trajectory and picks up a natural language description and tells you whether the trajectory matches the natural language description. So it's easy to train from any instruction following data that we happen to have lying around, like we saw earlier in the talk, and then adapt to new tasks in the same environments, but where we don't have instructions, by just doing inference over the space of goals implied by those natural language instructions. Now, why might this be a good idea? Well, there's tons of structure in the space of strings that we don't get in other places. Language makes it hard to describe weird, maybe sort of overfit sounding goals, like you want the third pixel in the observation image to be this precise shade of blue. So to the extent that we think real world RL problems are going to involve natural goals, language gives us a sort of natural description length prior on that space of goals. Very briefly, just as before, framing RL as inference of goal descriptions. You can do well at some of these complex grid world RL tasks we were looking at. You can do this for imitation learning, where you wind up with something that looks like programming by demonstration, where your programs now take the form of natural language strings, and the interpretation, the execution of those semantics of those programs is learned. So, for imitation learning, we have some fun experiments in the text editing domain as well. I want to conclude this talk a little bit more speculatively. So a common feature of the two families of models that we looked at today is that part of the model is a distribution over strings. In the options framework, we have some sort of high-level policy placing a distribution over sequences of commands that look like sentences. In the goal inference framework, we have a prior over goals that's just a prior over natural language descriptions of goals or of reward functions or what have you. Now, if you've been paying attention to NLP in the last couple of years, you've probably noticed that we are now really good at placing probability distributions over natural language strings. That is possibly the only thing that we really know how to do anymore. But this we can do quite effectively. So, we have these models with names like BERT and GPT and Elmo that learn to generate language either unconditionally or conditioned on other language data in various forms. And if you take these models and you train them on big text corpora, they are able to pick up a lot of information about how the world works, both common sense knowledge like the color of a banana, but more relevantly to our purposes today, information about the structure of actions or transitions in the real world. Like the fact that a knife is useful for chopping a carrot, that if you drop a glass, it will explode. And one thing that you could imagine doing in response is to say, okay, let's then just encode the entire world in text and take actions by exploring as best we can in those worlds. Those of you who grew up with a certain era of video games will recognize this problem that we've described as a text adventure game, right? Where some human designer has already gone in and built a whole representation of the real world in text. And we just need to reason about language in order to figure out what to do there. Sure enough, if you take one of these big pre-trained language models, you fine-tune it a little bit, you can do very effective exploration and play in these text adventure games. But to take a step back here, even if we ultimately care about not these kinds of text games, but about taking actions in the real world, and we can't hope to write down these kinds of text encodings by hand, we are still soon going to find ourselves in a situation where we have these ungrounded language models, just like distributions over sequences of strings that nonetheless capture a lot of the important high-level structure of like the MDP, right? The sort of real world of things and agents in which we all spend our lives, in which we want to build effective robots. I think this is clearest in NLP, but we're not far from having similarly rich models of vision and video as well. And in this perspective, the RL problem that we in language understanding like most desperately need a solution for right now is this. I have an abstract model that in some like very coarse and very noisy sense is isomorphic to the real world. But I have no idea about the actual correspondence between pieces of this model and pieces of the real world, right? I know what a glass is. I know if I drop a glass, it's going to break, but I don't actually know how to recognize one if somebody shows me an image of a glass. So how do I efficiently discover that correspondence, or at least the pieces that are relevant to my needs as quickly as possible? Like, how do I do model-based RL when the model that I have is only up to isomorphism, a model of my environment? So I think that's the big challenge for language and RL, something we're going to be thinking about a lot in the next couple of years and would love to discuss with all of you. Yeah, and that's all I have. If you're interested in these issues, a bunch of us put up a survey last year on the sort of NLP and RL landscape, and there's a bunch more pointers to related work in there. Thank you.
Thanks, Jacob. Yeah, this is really interesting. It touches some of the core issues in AI. Now we have a few minutes. We can turn the floor to questions. Open the floor for questions. I see that Chaba, you seem to have a question. Would you like to ask?
Sure. Hey. I was wondering while listening to the talk, to what degree the fact that you're using natural language is important. So I'm thinking about that. Obviously, if your task is related to, you know, like what humans would do, like place the scap here and there, and like finding natural text on the internet and using that as background knowledge is going to be important. But I was more thinking of the more abstract level of like, okay, I have a string of, I have a stream of strings, and like what properties should it have, how it should be, you know, like fit it to the language or whatnot in an abstract sense to the task. Do you have any thoughts about this?
Yeah, so, you know, I think one answer is that no, it doesn't really matter that it's natural language, right? That in these like policy sketches experiments we were talking about, this like barely qualifies as language. You could replace these with sort of arbitrary identifiers and still see the same effects. That being said, you know, like you said, once we want to start deriving priors from corpus data online, the fact that these things look like language is important. Another thing that we found, like especially in some of these text editing experiments, is that, you know, this idea that you have like a discrete space of say goal or task specifications or whatever, and then a learn function for interpreting them, sometimes lets you be flexible in ways that sort of starting with something that has formal execution semantics doesn't. So like for some of these string editing tasks, you actually do better here than if you try to just do like program induction from these examples. So I think, you know, I guess one question is it important to get language versus some other like ungrounded structured description of what you're trying to do there, I think only to the extent that a prior is involved. Another question is, would you do better at some of these tasks if you started with a language where you like already knew the formal execution semantics ahead of time with something like LTL or some more freeform programming language? And I think there it's actually not obviously the case, and that being able to learn the interpretation of these goal specifications buys you some amount of expressive power.
Mm-hmm. All right, cool, thanks.
Well, I have a related question, Jacob. In your talk, when you have language sketches or hints for the policy, it has concepts like wood and stick. Do you assume that these concepts are known to the agent beforehand so that you can efficiently map the instruction to the real objects in the environment?
Yeah, no, so for, where are unfortunately. Like for these experiments, no.
Right.
And you could certainly imagine, doing some sort of pre-training thing or getting like image captioning data for real tasks that involve these things. But yeah, no, the whole point here is that you know nothing about the semantics of any of these instructions prior to execution.
Interesting. So where is the signal for the agent to learn from these instructions to map it to the objects? Then let's say get. Then what? How is it different from get forest? So where's
sorry?
Oh, yeah. My question is, how does the agent get signal to learn to distinguish wood from saw and from other objects?
So here, from the fact that it's a multitask learning problem and that it's like shared by the prefix of these two tasks, or of the trajectories that you want to execute for these two tasks.
I see. So some kind of pre-training or transfer is required.
Yeah, I guess transfer more than pre-training, and again, like weight sharing more than anything else. That there's some structural constraint that says basically like I'm only going to, so one set of experiments that I don't have here is you can say, let me give the agent now like a sequence of these high-level sketch pieces that it's never seen in that sequence before. Can it learn to execute those successfully? In other words, have these like actually disentangled the behavior that they were supposed to disentangle, or are they all totally co-adapted to each other in these problems? You do a little bit worse in that setting, but still significantly better than any of these baselines. And so, I think the point is just that and I think I only have like a good sort of empirical account of this, but when you have a multitask learning problem like this, like this one that we have on the slide right now, and you say, the policy for each of these tasks is going to like do the same thing in both of these environments for some amount of time and then turn itself off and then switch to doing something else. That is enough to actually like learn a shared reusable behavior for the thing that is shared between the two tasks.
Cool, thanks. We have a question from the audience. Jacob, can you see the QA tab?
Yeah, so this is, can the policy sketches with respect to hierarchical policies and deep neural nets be handcrafted for which the text corpora is limited? So I guess the question here is, could you imagine writing down low-level implementations of these behaviors as a surrogate for trying to like learn them via RL in the setting that we've been looking at here? And I think that's basically this picture, right? Is can we, the hardest thing you can imagine doing is like literally baking into the weights of your neural net or whatever, an implementation of the getting wood behavior. The next easiest thing that you can do is build a like subtask completion classifier. And again, the point that we're trying to make here is just that you can get away with much weaker supervision than or much less work than either of these things if you just use this ungrounded sketch information.
I do have a question, but let's see whether other people have questions. Well, maybe I can ask my question then. It's not completely related to this talk, but it seems that here you're using natural language or some kind of language to assist reinforcement learning, efficient reinforcement learning. But there's also the opposite way where people use reinforcement learning to help NLP problems, in particular conversational systems, which is more like the languages applications. Could you say something about the connection of these two? Are they very different problems, or how they may be connected?
Yeah, no. So I mean, they're very closely connected to each other, and I think the biggest or the clearest example of that is on these kinds of problems. So right here, you have an agent. If you just think about the high-level learning problem, that is taking actions in a string-valued action space. Those actions are going to have some effect. Here, the effect is that they cause a different sort of low-level agent to do something, and then you get rewards based on that. In a conversational system, those actions like cause the person that you're conversing with to conclude that their request was satisfied, or to get annoyed and press the bad robot button or whatever. And so certainly there are like generic things that you can imagine doing to just like improve our ability to do exploration in these kinds of string valued action spaces that would be helpful in both of those cases. Another place where this comes up is, you know, if you think about these kinds of games again, one interesting question is, once I start to simultaneously train the thing that's picking high level actions and the implementations of those actions, do those actually remain consistent with the semantics of natural language or not? And this is, again, a problem you also have in these conversational systems, insofar as one way of training a conversational system without humans in the loop, which is really expensive, is to just like set up two chatbots and have them talk to each other. And there have been a bunch of there's been a bunch of work on that problem that's found in various settings that you very quickly diverge from anything that looks like the semantics of natural language. And, you know, these agents just start sort of sending gibberish to each other that's somehow meaningful to these learned policies, but totally incomprehensible to a human. And so again, I think, you know, one interesting question here is, when you have these like language valued action spaces, and you want to do RL in them, what do you have to do? What constraints do you have to impose on these models or on the learning process or whatever that allow you to like deploy strings more effectively while remaining faithful to the semantics of the language that you started with?
I see. Cool. Thanks. Yeah. Yeah, this is excellent. Thanks again, Jacob. Now I think it's time to move to the